Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Panama Buena Vista Union School District, and Kern High School District, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.
Well, good afternoon and welcome to Do the Math. I'm Michael.
I'm April.
There you go. There you go. We'll wait for
Julissa.
Julissa. And in studio with us, we have Julissa. Julissa, if somebody needed to contact us, what would they need to do?
For math homework help, call in Bakersfield 636-4357. Anywhere else, 1-866-636-6284. Email dothemath@kern.org. We're online at dothemathonline.net and on social media, Facebook, Instagram, Twitter, and YouTube.
All right, nicely done. So where do you attend school and what grade are you in this year?
I attend William Penn Elementary and I'm in 5th grade.
And I found out yesterday that they are the Penn Panthers.
Yes.
That was from Jacob. You know Jacob, correct?
Yes.
All right. So you typically, after school, what do you normally do?
After school, normally I go to after school program.
And what kinds of things do you do there?
We do homework and art and PE.
Okay, so you like doing all those things, right? It's pretty fun. You go after school, you get to do a little bit of art, a little bit of PE, take care of your homework. Do you have homework every single day?
Yes.
Is it a lot of homework?
No?
All right, so it's just a little bit. All right, and how is 5th grade going so far?
5th grade's good so far.
What do you think is the best thing about 5th grade so far?
Learning new things.
Such as?
Math.
So you like the math. What kinds of things have you done this year? Do you remember any of the things you've done?
We've mainly done fractions.
Okay, so you've done that a lot. And are you comfortable with fractions? Do you know any vocabulary that you can use with fractions? Like, we know there's a bar that separates the two numbers. You know what either of the numbers are called?
No.
Does numerator sound familiar at all?
Yes.
Do you think that's the top bottom or bottom number?
The top.
There you go. What do you think? Do you remember it? So numerator's on top.
Denominators.
There
on
you
the
go.
bottom.
See, so you remember, right? You just need a little spark right there, okay? What about equivalent fractions? You know what that means?
Yes, those are fractions with the same denominators.
Could be, right? If I had 4/6, 4/6, what would be an equivalent fraction to that? What would be equal to 4/6? So one way to do it easily is to multiply both numbers by 2 or divide them by 2. So if we had 4/6,
2/3.
2/3, right? That's an equivalent fraction, right? So all of that stuff is kind of the vocabulary that goes with fractions and mathematics, all right? Have you ever seen the problem of the day?
No.
No, well, because you're not on social media during school, I hope. So on social media, we do the math. We have what is called the problem of the day, and we're going to take a look at that right now, right? So let's take a look at the problem of the day and see what it was for today. So it says, simplify the expression. Have you worked on expressions at all like that?
I don't think so.
Okay, so taking a look at that, what do you think might be one of the first things you would want to do with that?
1 + 2.
Okay, and that's pretty simple, right? That's in parentheses, you can do that. So that's 3. So now what else would we have to do? Because we had 10 parentheses 3 plus some other stuff with letters. What do you think we would do then?
Add 3 with 10.
Okay, so if there's parentheses, the 10 outside of it means we're going to multiply whatever's inside the parentheses. So it's going to be 10 times whatever's in there. So what do you think that would be if there was 3 inside of that?
Then you would times it by 10.
And what would you get?
30.
30, all right. And now we have plus 9v plus 7v. So what do you notice that's different about those?
The letters.
Right, they have letters. Those are called variables, right? Because we don't know what they stand for. Now, do you think you can put 9v with 30? Or do you think you should put 9v with 7v?
9v with 7v.
Why?
Because they're next.
Okay, they're next to each other and they're alike. How are they alike?
Because they're closer to each other than 30.
True. Any other way that they're alike? So think about 30, 9v, and 7v. So why would we put 9v and 7v together instead of 30?
Do you hear something that they both have in common?
So here they are. 30, no letter. 9v, 7v.
Well, because the one doesn't have letters and the other does.
The others do, right? Okay, so I know you haven't done this before, right? So let's take a look at it one more time. So you know that the first half is 30. Now, if we have 9v and 7v, what will we get with that?
46.
Well, you're multiplying them, right? So I think that's what you're trying to do, right? Just think about if we have 9 apples and 7 apples and we put them all together, how many apples are we going to have?
16.
16, right? So it's the same thing with the V, it's just a letter, all right? So the answer to the problem of the day is 30 plus 16V, option A, so there you go. So your first step with expressions, right? So guess when you're going to do those?
Maybe later on in 5th grade?
Maybe later on in 5th grade, but you're going to do them in 6th
Sixth
grade.
grade.
All right, so if you kind of remember that a little bit, it'll be something that you'll be getting ready for, all right? So you are going to have an activity today, and have you ever heard of a fractal?
No, not before.
Okay, so we're going to learn a little bit about fractals today, what they are and what they look like. So this is a fractal right here. What you're going to do is you're going to be making a Sierpinski triangle fractal today.
Okay.
All right, so we're going to start off with one big fractal. And what we're going to do is we're going to show everybody back at home the directions to this so that they can see what they have to do, okay? So it's basically, they're starting off with a large triangle. And the midpoints are already labeled in each of those 3 lines. And what you're going to do is you're going to connect the midpoints and make a new triangle, okay? And from there, you now have a triangle up here. You're going to connect the midpoints and make a new triangle.
Okay.
Sound good? And you're going to keep doing that over and over, and you'll see what kind of starts developing. Sound good? All right, so we're going to let you go ahead and get started on that. So here's a couple pencils. So the first thing I would do is probably connect those 2 midpoints. All right, so go ahead and, why don't you take care of that first? So just make sure you hold the rulers steady, and then you can just go ahead and draw that line. There you go. So now you need to connect those 2 dots with that one. So how will you do that?
Like that.
And you can move whatever you need to so it's comfortable and you're able to do everything. There you go. Good. Okay, so that's the first step. So we had a large triangle, and then you connected the midpoints, and you have a smaller triangle in the center. Okay, so now what you're going to do is, while we go away for a couple minutes and take a look at some NASA stuff, you're going to find the midpoints of the lines and keep making smaller triangles.
Okay.
Sound good? Then we'll go on to the next step. All right. So before we do that, let's first take a look at today's Math in the News. All right, today's Math in the News has to do with exactly what we were talking about, fractals. Have you ever heard of the word fractals before?
No.
No. Okay, so this up here, does that background that look kind of cool? You like something like that?
Yes.
It does, right? That's a fractal right there. What do you notice about that?
It's repeating over and over again.
There you go. You have the key word. It's repeating over and over again. All right. So this is something you're probably going to do when you're in middle school also, and when you get into geometry in high school, you're probably going to be working with this a little bit more. All right. So mathematician Mandelbrot, he coined fractals from the Latin word fractus, fragmented, right? In 1975. So they're visual expressions of a repeating pattern, just like you said, right? The pattern repeats itself over and over. So this is the Mandelbrot set, and you can see how you're starting with one shape, and then you're going to find the midpoints, and you're going to keep making that shape over and over again. Can you see that a little bit there?
Yes.
All right, so some of these you might be able to see a little bit easier. There are fractals in nature, okay? So I'm sure you've seen flowers before, right? Even sunflowers and things like that. This is a type of succulent, like an aloe vera type of plant, right? Doesn't need a lot of water. This is a type of fern and snowflakes. Have you ever been in snow?
Yes.
Okay. Did you see yesterday's show?
Yes.
You did. So you learned a little bit about snowflakes too, right? All right, there you go. See that? You're all over it. Good thing you watched yesterday's show. So that's why we're doing fractals today, because snowflakes had patterns and fractals goes right along with that. So these are fractals, and some of these are computer generated. So you can, once you learn how to code in a computer, you may already know how to do this. Do you know how to code at all in a computer where you can set something up and it does a couple of steps for you at one time?
No.
Okay, well guess what? You're in middle school for 6th, 7th, and 8th grade. You're going to be doing some of that also. This sounds like a lot of fun when you get to middle school, doesn't it? You're going to be doing a lot of things, all right? So you'll be doing some fractals, and some of these are computer generated. And let's go ahead and take a look at another one. So here's one where they simply started with what looks to be the trunk of a tree, right? You're just starting off with a V, right? Anybody can do that, right? But then when you get at the ends, you start making other V's, right? That seems pretty simple, right? Then at those ends, you keep going like that, and you keep getting smaller and smaller until eventually you do it enough times, you're going to end up with something that looks like that, right? So you've got some other fractals here, and remember how we were talking about the fern, right, in nature? So here they are. And what does this and this remind you of?
Snowflake.
Snowflakes, right? And here, what does this remind you of right here?
That reminds me of this.
The one that you're doing on the paper, right? The Sierpinski triangle fractal, okay? And then we can see right here, these are some different iterations. So this is what you're doing. And here's one where we're starting with a triangle, but instead of doing them inside, we're doing them outside. So we're putting another triangle in the center of this line, right? And then in the center of this line, we're going to put a triangle, which is what you see right here. Okay, does that make sense? How you just keep getting smaller and smaller going around, and then eventually, starting from one triangle, you get something that looks almost like a snowflake, right? And these are beams, and you just kind of do the same thing. And there's just a whole bunch of different patterns that you can do with fractals, and just that, as you said, that repeating pattern over and over and over again. So that is today's Math in the News, a little follow-up with fractals and how they tie into snowflakes from yesterday because of all of the weather that we've been having. Have you had any problems with the rain? Because it's been raining a lot. You've had some problems with the rain?
It's been raining a lot.
Yeah, it's been raining a lot. Have you been stuck in the rain at all? Like it's made life more difficult for you?
A little bit.
A little bit? You know, some people, they don't like driving in rain, adults and things like that, but as far as you're concerned, it's just trying to get from one place to the next place kind of dry probably, right?
Yes.
Okay. How about your school? I know that at our school there are some low spots when kids are walking around from classes outside, and it seems like you've got to go a long way around to get around the deep puddles and stuff. Is that happening at your school a little bit? So maybe you can talk to somebody at your school. Maybe you can talk to Mr. Dillard over there and go, hey, you know what? I know that I'm leaving next year, but maybe you guys can fix up the grounds a little bit for next year's kids. Sound good? Are you involved in anything at school? Do you guys have any clubs or activities or sports or anything like that that you do at school?
I don't do any of them, but there are a few clubs.
But you do the after-school thing.
Yeah,
And so, do you like doing art or PE more? If they said you can do either one today, would you do art or PE?
PE,
Why?
because I like to move around.
You like to move around and stuff, right? Now, if they said, all right, you can either do PE or you can do more homework.
PE.
Okay, good. That's what I would say too. I would say PE also. 636-4357 is the phone number. We do have phone tutors available until 5:30 most Tuesdays and Wednesdays throughout the regular school year. And as promised, we will check out a little bit of what NASA has going on.
Welcome to the International Space Station. I'm astronaut Aki Hoshide.
I'm astronaut Megan MacArthur. Today, we're going to discuss how engineers design space station modules so we can use the entire volume to live and work.
What is volume? Glad you asked. Let's go check it out. Area is defined as the two-dimensional space occupied by a flat shape or surface of an object, whereas volume is the amount of space occupied inside a three-dimensional object.
Length times width will give you the area of a square. Take the area of a square and multiply that by its height to get the volume of a cube. For example, here's a cube that is 2 meters long by 2 meters wide by 2 meters high. Multiply those dimensions and you get 8 cubic meters of volume. But that's only one way to calculate volume. Cones, cylinders, and spheres all have different formulas to calculate their volumes. To calculate the volume of a cylinder, we take the area of the circle, pi times the radius squared, and multiply that by the length of the cylinder. In the Destiny module, we have a pressurized volume of approximately 106 cubic meters, or 3,700 cubic feet. That's a lot of space for us to live and work.
Destiny is the primary research lab for U.S. payloads, supporting a wide range of experiments and studies contributing to health, safety, and quality of life for people all over the world. Engineers designed these cylindrical modules for astronauts to utilize the entire three-dimensional space.
So you've learned that Destiny is a cylindrical-shaped pressurized module, but inside the space you can see that our interior space is a little bit more like a square. So these racks are designed to fit against the walls of the circular cylindrical module, and so the back of the rack is curved and the front of the rack is straight. And so we can keep a variety of different kinds of experiments in different racks, and we can also use the ceiling and the floor just as easily as if it were a wall. So one of the places that we store some of our stuff is in the ceiling. You see we have these different kinds of bags that we store things in these different kinds of cupboards. We also can keep our medical kit up here out of the way. So if anybody gets a cut or a scrape or needs some medicine, we have different packs in here that have all the different things that we might need while we're up here. I can also use space in the floor. We actually have a window that's in our floor that looks straight down onto the earth. I hope you learned a little bit about the importance of engineering and utilizing volume aboard the space station today. Use the corresponding classroom connection to learn more about area and volume and challenge yourself to redesign your own home and classroom for life in microgravity.
Maybe one day, you will be an engineer designing rooms for us up here in space. See you next time.
And the next generation of explorers, we have one right here, Julissa, a 5th grade student from William Penn Elementary, working on your Sierpinski triangle fractal. So let's see how you're doing so far. So when we started, there was one triangle, and you drew one big one in the middle. How many triangles do you have now?
4.
You have more than 4 triangles there. So let's count them up. Right? Any triangle at all.
14.
14, that's a lot from 2, right? Okay, so now for the students watching at home, you're going to find the midpoints of these lines. So go ahead and draw another triangle up there. And you said that the fractal, what you were doing, right? So go ahead and find the midpoints of those 2 lines and then draw another triangle. Was a repeating pattern, correct?
Yes.
And that's what you're doing, right? You're continuing this pattern of drawing triangles by finding the midpoint of every line. There you go, straight across, and that way you'll know you're at the same height. How many triangles do you think you'll eventually end up with when we're all through with this? Because you went from 2 and then you had 14. How many do you think you'll end up with?
Maybe around 20.
You think around 20? All right, well, you know what? Finish up that triangle right there. And what you're going to be able to do also is you're going to start coloring these so you have some sort of a pattern also with color. So I want you to start thinking about how you would like to color these. But right now you're doing art with math. Does that make sense?
Yes.
Right, you're doing an artistic piece, making a fractal with mathematics. But you said you were working on fractions in class. So let's take a look at your homework right now, and we'll help you out with a couple of these real quick. So, ladies, over to the board. If you want to, you can go ahead and write these fractions up on the board. So the first one we have is 9/16, so 9/16. And the next one we have is 12/15, 12/15. And the last one is 1/10. And they're saying they are approximately equal to. So what they want you to do is they want you to round each of those to 0, 1/2, or 1. So as you're doing it, Julissa, explain to April what your thought process is as you do it.
So, the first 9 out of 16, 9 is closest to 8, and 8 divided by 2 is 16, so it would be around 1/2.
Okay, so 8 times 2 is 16, right?
Yes.
And so it's going to be 1/2. So what's going to be 1/2? 8/16?
9/16.
Is 9/16 1/2 or 8/16 1/2?
8/16.
So 8/16 is 1/2. So 9/16 is close to 8/16. So it's going to be about 1/2. Okay, so can you write that there? Because we are trying to see if the numbers are close to 0, 1/2, or 1, right? Okay, so because 9/16 is close to 8/16, and you know 8/16 is 1/2, you know that that's closest to 1/2. So what about 12/15? What can you tell me?
12 is only 3 away from 15, so that would mean that it would be around 1 whole.
It'll be closest to 1 whole because the unit fractions left, there's only 3. And how big of a piece is 1/15?
15.
There's-
Or 1.
But use your fingers, like how big would a 1/15 be?
Like that big.
Yeah, it's going to be a tiny piece, and so it's only three tiny pieces away. So that's going to be closer to 1 because 12 is 3 tiny pieces away from the 1. Okay, you can go ahead and write that there. And what about 1/10? What will that be?
1 is closest to 0, and 0 out of 10, well, that's nothing, so it
Okay.
would be 0.
It would be 0 because if you have 10 parts and 1 is on this end, it's going to be closest to 0, so that's going to be 0. Very nicely said.
There we go. Those are the first 3 right there on your homework, so we've got those out of the way. So clear the board, here come 3 more. But we're going to be doing something a little different with these ones. You want me to just erase that board for you?
Well, doesn't she have to write them later?
Do what?
Yes, you can erase it. I said,
No.
doesn't she have to write them later?
Not those ones.
Okay.
All right, so here we go. So the first one we have is 5/9 plus 1/9.
You can go ahead and write that. 5
So
ninths.
5 ninths plus 1 ninth. And we'll just do these one at a time. So it says add them, and then they want the sum in simplest form. So if you could explain what sum means and simplest form.
Sum means like the amount after once you add it,
Okay.
and how you do it is first you have to find out the answer, which you only add the numerators.
Why are you only adding numerators?
Because if you add the denominators, then it'll be too much.
Okay, and the parts are the same, right?
Yes.
Because we want like things like the V's we talked about earlier. So since those fraction have the same number of parts, we can go ahead and just add the numerators. But the key is, can these numbers be the same, or can these numbers be different, or do they have to be the same? The denominators.
They don't have to be the same, but it's easier if they are the same.
Okay. So because they are the same, we're just going to add the numerator, keep the denominator. Go. And so the second part of the problem was to write this in simplest form. What do you know about 6, the number relationship between 6 and 9?
3.
They're both divisible by 3? Okay. So if you divide the numerator and the denominator by 3, what will you get?
You would get 2/3.
Nicely done.
Let's take a look at the next problem. We have 1/7, so 1 over
You wanna
7.
write
You
this
just write it down on the bottom. Plus 6/7, 6 over 7.
So first you would add 6 over 6 plus 7, and then you keep the denominator, which would be 7 over 7. And 7 is the same exact number as the bottom number, so it would be 1 whole.
So do you know what this bar stands for? Like, we talked about numerator, denominator, but do you know another way to say this? 7. Do you know that this says 7 divided by 7?
Yeah, my teacher talked about it.
Okay. So what is 7 divided by 7?
1.
And there we have the 1 whole again. And so we simplified that to 1 whole.
Now, you know how that came to be?
I do not.
What I want you to do, Julissa, over next to the 1, I want you to write out the word divided by. So write divided. Well, spell it out. D-I-V-I, all that. D-I, V-I, D-E-D. And then by. So divided by. Now, that takes a long time to write that, right? So
Yes.
if you, do you know how to write in cursive yet?
No.
Okay. What I want you to do is underneath that, I want you to write it the same, I want you to write divided again, divided by, but I want you to write it as fast as you can. All right, go. Faster. Okay, now do it again, and I want it done faster this time, okay? When I say fast, that's what I mean. Go.
Fast, fast, fast. Go.
Fast. I mean, come on, fast, let's go. You should be done. Come on, let's go. Go, go. All right, I'm going to give you one more opportunity. Okay, I want it done fast. You ready? On your mark, get set, go. Fast, fast, come on, go, go, go. All right. Now, what do you notice about every time you did it fast? What do you notice about your handwriting?
They're starting to get sloppier
They
and
got
sloppier.
sloppier, right? So you know what they did after a while? They just put a line. That's why you get that fraction bar line. Because it means 7 divided by 7. But they didn't want to keep writing divided by in between that all the time. So they kept going sloppier, and then just make a line. That means divided by. Make sense?
Yeah.
All right, Hotshot, let's clear the board. We'll get you to do some other problems here. All right. So now we're going to take a look at, because you've been working with the same denominators, now let's make them a little different. So we have 1 over 6 plus 7 over 12.
Me? Okay, so we were talking about, can I add them because the denominators are different? And so here I have 1/6 and here I have 7/12, but they don't have equal parts. So in order to add them, I have to make sure they have equal parts. So earlier, we talked about equivalent fractions and finding equivalent fractions. So is there a number that I can multiply 6 by to get 12?
2.
2. So I can rename this fraction so that it has the same number of parts. So if I were to rename 1/6, multiplying the numerator and the denominator by 2, what would its new name be?
2/12.
So go ahead and write that there. And then to that we'll add 7/12. So there is a rule. In order to add fractions, you do have to have the same denominator. So I can't add the denominators, I can't add the fractions unless the denominators and the parts are equivalent. Okay? So talk to me about how we do this.
Well, first you just add 7 plus 2, which is 9.
And we keep the same number
You
of
keep
parts.
the same denominator.
And is there a number relationship between 9 and 12? Can you think of a number?
3.
Divide the numerator and the denominator by 3.
Oh, wait.
And then can you make that 3 over 3? Or 3 divided by 3? So if I'm dividing the numerator by 3, I have to divide the denominator by 3. 3 divided by, okay.
4.
Great job. Can we go any smaller, or are we at this?
We're done with that.
We're done with that? Okay.
All right, nicely done. So you've done a lot of great problems right there. And for your efforts so far today, you've got yourself a meal courtesy of our friends at Grillin' Burgers. So congratulations on that. When you go to, have you been to Grillin' Burger before?
No.
All right, well, this is going to be a treat for you, young lady. When you go there, you're going to ask for Lydia. All right? Lydia loves do the math, and she'll set you up with whatever kind of meal you want. All right? Sound good? We do have phone tutors available until 5:30, and we're going to get Julissa working on her Sierpinski triangle fractal again, and we'll do that while we take a look at what NASA has for us now.
Hello, my name is Tom Marshburn,
And I'm Matthias Maurer.
and we're astronauts living and working aboard the International Space Station, orbiting 250 miles above the Earth's surface.
In the not so distant future, we'll be sending astronauts on missions that go deeper in space than we ever have before. To do that, we'll need to design transportation systems and habitats able to meet our needs. Engineers are designing, building, and testing these systems right now.
You may be wondering, how do they achieve this, and what steps do they take? The engineers use what's called the engineering design process. This process involves a series of steps to guide them in developing a solution. Each piece of technology on the space station and in your home or classroom involves engineering. But what exactly do engineers do? Well, they use science, math, and their own ingenuity to create solutions to technical problems. Examples of technical problems could be developing more efficient light bulbs or vehicles, lighter sneakers or aircraft, an orbiting space station, and transporting humans to Mars.
Here's one example of what the process looks like.
Step 1, identify the problem. Step 2, identify resources and constraints. Step 3, research. Step 4, develop solutions. Step 5, select the best solution. Step 6, build the solution. Step 7, test and evaluate the solution. Step 8, record and present the results. And step 9, improve the solution.
Take a look at the space that we are currently living and working in. This space is filled with things that have been engineered using the engineering design process. Some of these items are low-tech, like packaging, storage compartments, and fasteners. And some of these items are high-tech, like computers, cameras, and science experiments.
A great example of an engineering solution to something you might be surprised is a problem in microgravity. How do we drink fluids? How do we keep them contained, and how do we get them in our mouth without making a mess everywhere? Here's our standard drinking pouch. I've got some grape drink in here and a very nicely designed straw. It's just perfect for living in space. If we didn't have this straw, start to see some fluid coming out there. I don't want to make too big of a mess, so I'm only going to demonstrate what would happen for a second if we didn't have our straw here. And this would come right off. And it's getting on me right now. So let me drink this up. But as you can see, we have a clasp here, very nicely designed. It pinches the straw at this point here, and that keeps more fluid from coming up the straw. And that way, if you want to drink something, you just open it up when you need to drink. You have to remember to close it again before you pull it out of your mouth. Otherwise, you're going to get more fluid coming out.
Hey, Tom, you're floating. I think that's not convenient for working, no?
That's true. Got a little bit of a problem in that if I do any work with my hands, I'm going to be pushed away from where I'm working. And if I have to find a place to put my feet, which I really want to do in order to get any work done, sometimes I can't find a place to put my feet. Still working on it. So I got a problem.
Based on astronauts' feedback and data, we developed these rounded hand and foot rails so that you can stay in one place comfortably for short periods of time. To maximize comfort, we also have these socks that are padded with rubber on top and bottom. For longer periods of time in one workspace, we engineered these foot restraints with cloth straps. You can slip right in and adjust them.
Thanks for exploring the engineering design process with us.
I'm going to send it back to Earth so you can solve your own engineering problems using this process.
See you again soon.
Well, I tell you, there's nothing like live TV, especially when you've got a bunch of people helping you out all the time knowing what's going on. So they must think I'm a little older than I actually am. They're all looking at me like this. But anyway, I do appreciate all of the help. And as a matter of fact, this is a perfect opportunity to say, as we are in our 21st season of Do the Math, just a thank you to everybody behind the scenes, because it's just not April and myself up here and other hosts and things like that. And the students are certainly the star of the show every day. But it is the multitude of people that are behind the scenes that actually make this program work. So we want to say thank you and commend all of you for helping out with the program during our 21st year. So Julissa is a 5th grade student at Penn Elementary, and you've been working on your Sierpinski triangle fractals. And as soon as you draw those lines for the last triangle that you're doing up on top, let's move this ruler away and see what you've been doing. So you started off with one big triangle,
Yes.
right? You made the one in the center, you had 2. When you counted them last, you had 14, right? Now you're starting to do a little bit of coloring for your pattern. So explain to us what you're doing with the colors and how you come about this.
I'm doing green and red over and over, and I chose that because I like Christmas.
All right, so you like Christmas, right? So green and red are the colors to go with. And since you colored in the first bunch of them, you started making other smaller triangles. And you had thought that you were going to end up with about 20, correct?
Yes.
All right, so what we're going to do is we're going to have you stop right now, because we'll have another opportunity to keep adding to this, but you have some more homework to do, right?
Yes.
All right, so down with the pencil, back over to the board, young lady. Here we go. One of the problems on the back of your paper is Mike spent 11/12 of an hour. That is a long time, right? Because if you were estimating, Julissa, 11/12, is that closer to 0, a half, or 1?
1.
1. That's like saying somebody was on the phone for a whole hour, right? So Mike was on the phone for 11/12 talking on his cell phone. Brent spent 7/12 of an hour talking on his cell phone. How much more time did Mike spend on his cell phone than Brent?
Okay.
So why are you subtracting?
Because it's asking how many more, so you have to subtract.
Okay. So are we going to do anything different aside from subtraction?
No.
Denominators have to be the same?
Yes.
Yes. Denominators have to be the same, are they?
Yes.
Check. So now we can do what?
Now we can subtract them.
And what are we subtracting? What part of the fraction?
11 minus 7, then numerators.
The numerators. Okay, go ahead. And are we done yet? So 11 twelfths minus 7 twelfths is 4 twelfths. Is there more we can do?
We can simplify.
And what are you thinking of dividing
2.
by? Okay, let's try that. Perfect. Are we done yet?
Yeah.
What kind of number is 2? Even or odd?
Even.
What kind of number is 6?
Even.
And what do you know about even numbers?
You can divide them by 2.
Every even number is divisible by 2. Go, let's have at it. Great job. So when we simplified 4 twelfths, we got 2 sixths. Realized we still had 2 sets of even numbers, and now we're at 1/3. Is there more we can do?
No.
Great job.
Now, before we go on, I do say that we have something else we can do. I'm going to throw this in there for you. Now, you've already got yourself a meal at Grill and Burger.
Yes.
Have you ever been to Chick-fil-A?
Yes.
Do you like Chick-fil-A?
It's good.
I'm going to throw in a meal for you at Chick-fil-A if you can do the next thing.
Okay.
Are you ready?
Yep.
It said that he spent 1/3 of an hour more. How many minutes is 1/3 of an hour so that we can compare this to minutes? So think about 1/3 of an hour. How many minutes would that be? So you and April go ahead and talk about that.
Is
a little
there
bit.
anything that you can think of that we might need to help us visualize 1/3 of an hour?
Well, I know that 60 minutes is an hour.
Okay. So I'm gonna write that because you said it. Okay, what else?
No.
Okay, so is there a way that you can find 1/3 of 60 minutes?
And see, April, this is going to blend in beautifully with what I want you to do with her next.
Okay.
Right? So you're looking for 1/3 of 60. And think about how you would write that mathematically.
You would put 60 as a denominator. And
So what exactly are we doing with this 60? If 60 is my whole, I want to partition it or break it into how many parts?
break it into
How many parts?
1/3.
So how many parts are in 1/3?
1.
So if I were to draw, give me thirds there. How would you break that into thirds?
Thirds is hard, isn't it? It's not like doing half, right?
I was thinking, I don't know. You want to use that? Can you break that one into thirds? So remember, when we break into thirds, what do I know about my parts? What did I say about these parts right here? They have to be
Equal.
So do we have 3 equal parts there?
No.
So how many equal parts do we have?
4.
So how would I make that 3 parts instead of 4 parts?
So maybe
you
go
wanna
back to the
box?
rectangle and try that one again.
Can you make 3 equal parts from that box? So how many parts do you have right now?
4.
Right here. How many?
0.
Okay, there's just one part, right? If you draw one line, you're going to have how many parts?
2.
Depending on where you draw it. If you draw another line, how many parts will you have?
3.
There you go. So if I have 60 as my whole, and I want to break it in parts for thirds, how many would be in each of these parts?
2.
2? So if I have 2 here,
Or 20.
20. So 20, 40,
40, 60.
60. So there's going to be 20. And if you're thinking about time, that's going to be 20 what?
20 minutes.
20 minutes. So 20 minutes is a third of an hour. So he was on the phone. How much more time? If we're talking about minutes.
20.
20 minutes more. Mike was on the phone 20 minutes more than Brent.
All right, well, you know what? Since you got 20 minutes, and I did say we throw in some Chick-fil-A for you right there, you've got yourself a meal at Chick-fil-A also, so not too bad of a
2
deal.
meals.
So when you go to Chick-fil-A, if you happen to remember, say, is Troy in? And Troy is the one that owns Chick-fil-A, and he loves to do the math as well, and he'll set you up with a meal over there also.
Okay.
All right, that's not too bad. Do a problem, get a meal. Okay, so now what I'd like you to do is I want you to write 1/3 of 60 mathematically. So April's going to help you out where we're going to write 1/3. You know how to write 1/3, right?
Yes.
So put 1/3 of, just spell it out if you don't know how to do it mathematically, right? Just like that divided by eventually became a symbol, 60. So now April is going to start talking to you about multiplying fractions, which is what you're going to be starting to do in school pretty soon. But this is one way to kind of get you into that based off that last problem. All right? Take it away, ladies.
Okay, so if we're talking about 1/3 of 60, I'm going to take 1/3 and I'm going to multiply it by 60. So then it becomes 1/3 times 60. But I have a fraction here and I have a whole number here, right? And when we were adding, we had a fraction and a fraction, right? And if they were the same, it'll be easier to manipulate, right? So can you change 60 into a fraction? Can you change that whole number into a fraction? What is 60 as a fraction?
So here's a hint for you. I'm going to give you a hint. What's 2 divided by 1?
2 divided by 1 is 1.
2 divided by 1 is 2.
2.
What's 10 divided by 1?
10. I mean, 1.
What's, it's
Or
10,
10,
right?
yeah.
Don't overthink it, right? What's 24 divided by 1?
24.
Okay, what's 33 divided by 1?
33.
And those are all like 33 with a fraction bar over 1, right?
Yeah.
So how can you make that a
60,
fraction, where it's still going to equal 60?
60.
60 over,
1.
there you go. So, and then take a look at it and see if that makes sense.
60 over, the other way, 60 over 1. So what is 60 divided by 1?
60.
Did we change the value?
No.
Just the way that we just renamed it, right? The way that it looks. And so now I can beautifully multiply, because when I multiply fractions, I can multiply the numerator and get a number, and then I can multiply the denominator. And there doesn't have to be any likeness in multiplication. I just multiply the numerator, multiply the denominator. So what is 1 times 60?
60.
Go ahead and write that. That's our that's our numerator. Divided by, or fraction bar, and 3 times 1.
3.
And 60 divided by 3, we're going to simplify.
It's 20.
20 equals 20. And we just found 1/3 of 60 in a different way than we did with the hour.
So April, I'm going to give you guys 2 minutes.
Okay,
You can do whatever you want with multiplying fractions.
okay.
So if you want to do some sort of a model or anything, or just work on a simpler problem, but you have 2 minutes to kind of do a little something.
Okay, so this time we're going to use an area model, and we're going to do 1/2 times 1/3. Okay, so can you draw a rectangle for me? Or, yeah. Okay, So this is my hole right now, and I want to split that into halves. So where would you draw a line to make that halves?
In the middle.
And where would the shading be? So now can you shade 1/2 of that? Go ahead and switch the pen. So now I'm going to multiply by 1/3. So I split this into 1/2, so now we're going to go vertically. Let's go into thirds. And remember last time we drew 2 lines to make thirds. So equal parts this way. Let's make some thirds. Hold on just a second. Let's go horizontally this way. So is that equal parts?
No.
So we need to make 3. Remember last time we drew how many lines to make 3?
2.
2. So looking here, where can I split to make equal thirds this way? We're going to go this way with it. There we go. All the way across. Has to go all the way across the rectangle. There we go. So if you were to shade, this is 1/3, 2/3, 3/3. If you were to shade 1/3, can you shade your 1/3 for me? And all the way across the rectangle. All right. So now, where do you have both black and a red?
Right there.
Right there. So we have black and red in this section here, right? So that would be one of how many parts do we have in our rectangle now?
5.
Count them one more time. Count this one too.
7.
Count them one more time. Touch them when you count them.
1, 2, 3, 4, 5, 6. So 6.
6. So we just shaded one of 6 parts. So we just talked about how to multiply fractions, right? So does that follow that same rule that we did? What's 1 times 1?
1.
And 2 times 3?
6.
6. And this is why, because I'm going to take 1/2, then 1/3, and I'll have one of 6 new parts.
Nicely done. And using the area model and talking about what you just did, you timed it out exactly to 2 minutes. Nicely done. Maybe we'll get you a little meal at Chick-fil-A also. Hey, you know what? We have one more opportunity to check in with NASA. We'll be back with more right after this.
Hello, my name is Shane Kimbrough, and I'm an astronaut living and working up here on the International Space Station. In this demonstration, I'll be talking about the 5 main senses we have and how we use them up here on the station. Let's go check them out.
As humans, we have 5 senses that let us observe the world around us. These senses are sight, taste, smell, hearing, and touch. Our senses help us determine whether or not we like something, but they also warn us if something is wrong. Sometimes our senses pick up very good things, like the smell of fresh-baked cookies or the taste of yummy pizza. Other times, our senses may warn us of danger, like the smell of something burning or the feeling of something hot. Let's go through the 5 senses and talk about what we may observe with them up here on the station.
Sight.
The sense of sight allows us to see the world around us, or in my case, space. Here on the station, one way we use our sense of sight is to see different experiments we are working on, so we can report the results back to Earth. Some astronauts have noticed that their sight changes a little after living in microgravity aboard the station. Scientists are helping to fix this by conducting research up here on astronauts like me.
Taste.
Our sense of taste comes from our tongue, and it tells our brain what kind of food and nutrients we are putting into our body. We can tell when something is super sweet or very salty because of this. Because of fluid shifts on the space station, sometimes our noses can be a bit stuffy and it can be harder to taste food. So lots of us love to add hot sauce to many of our meals to amplify the taste.
Smell.
Just like with taste, sometimes our sense of smell can change up here in microgravity as the liquids in our body move around. Once our bodies have adjusted to microgravity, the space station has a very distinct smell.
In terms of hearing inside the space station, there is constant noise coming from the different machines that keep our air flowing and the experiments running. Our sleeping quarters block some of the noise, though, so we're able to get a good night's sleep each night. What do you think you would hear outside the space station? Well, you better be wearing a spacesuit, so you'd be hearing the fan noises inside the spacesuit. But if somehow you were able to be outside of that spacesuit, you would hear absolutely nothing, because sound cannot travel in space because it has no air to travel through.
Touch.
Usually when you think of touch, you think of observing how things feel with your fingers. Since we are floating, we are constantly having to touch and grab onto objects, either using our hands or our feet. You can use your feet to walk up here if you carefully hook them under handrails as you go, but this is pretty challenging, so we like to use our hands more than our feet while we're up here. We will often use our hands to move along and carry objects with our legs. Thanks for learning about the 5 main senses with me today. Start thinking about your 5 senses and how they help you observe and adapt to your environment down on Earth. See you next time.
All right, a lot of stuff coming out from NASA, and as they say, the last frontier, the final frontier, and a lot of students are very interested in space exploration and space science. Julissa is working on her Sierpinski triangle fractal, just about done putting the last triangle in with the pattern she's going with right now. And you said we started off with the 1, then you made the big one, you had 2, then we got to 14. You thought we would end up with about 20. So what I want you to do is start counting. How many triangles do we have now? Are you past 20 yet? Keep going. I didn't mean.
50?
You have 50 triangles? That's more than double what you thought they were going to be, right? So why do you think it jumped so fast like that? Because you were at 14 and you thought you were going to be at 20. How did it all of a sudden get to 50, do you think?
Because you're not only making more by drawing them, but because they're making more on the sides too.
Right, and they're getting smaller, so you're going to be able to fit more in there, right? Yes. Now, do you know what it means to be an ambassador?
No.
Well, I'm going to tell you right now. The first thing you do when you're an ambassador is you get to have a uniform. Have you ever had a uniform before?
Yes.
Well, this is your uniform that you're going to have from now on. So this is the Do the Math Ambassador uniform. So as you wear this to school, people are going to be looking like, hey, what's going on with that shirt? And I bet your principal, Mr. Dillard's going to go, it's a fine looking shirt right there, right? And he's going to say, what can you tell me about that? What can you tell anybody about Do the Math if you had to tell them in a couple of words?
Fun.
Do you get to learn things?
Yes.
And it's fun. Those are probably the 2 biggest things you need to know, right? Mm-hmm. All right. Do remember we have phone tutors available until 5:30 most Tuesdays and Wednesdays throughout the regular school year. Our newest ambassador, Julissa, a 5th grade student from Penn Elementary. And until we meet again, continue to do the math.
Major support for Do the Math has been provided by Chevron, the Kern County Superintendent of Schools, Edison International, Valley Strong Credit Union, California Resources Corporation, Panama Buena Vista Union School District, and Kern High School District, with additional production assistance provided by these supporters of education in Kern County and throughout the state of California.